Okay, so now we start our program, and the first speaker is Christian Bach, who will present talk on very complicated subject. Asymptotics beats Monte Carlo.
Okay, thank you very much for the kind introduction, and also thanks for this very nice opportunity to be here in Moscow. So this is, I think, maybe a little bit outside the, I mean, this is a bit different maybe than most other talks here, and also I know that several people here have already seen this presentation, so I apologize to them. This is joint work with Peter Lawrence, who recently passed away, sadly, so I continue to work on this. So what is the problem that I'm going to, I mean, generally the problem is we want to compute the price of an option like this. So S is some stock, and in this particular example, S is actually a high-dimensional vector of stocks, and the option is of this form, which is a basket option or an index option if all the weights are positive, but it could also be a so-called spread option when some of the weights are negative. Obviously, if all the weights are negative, then this is trivial because then this is just zero. So at least one of the weights have to be positive for this to make sense. And the focus here is on a high-dimensional situation, so when n is large. And how large could n be in practice? Well, for instance, for one of the most important indices, the S&P 500 index, n would be 500, so there are 500 stocks in the index. And in principle, if you're facing a problem like this, there are, I would say, 4 different approaches. So there are PDE methods. So I mean, by the Feynman-Katz formula, this function here satisfies a partial differential equation, and you can solve the partial differential equation using finite element or finite difference or some other methods. And this is quite fast and also general, but it's fast only in low dimensions. So there is the curse of dimensionality, which says that, you know, if the dimension is bigger than, say, 3, 4, maybe 10, if you really use some sophisticated methods, you can maybe push it a little bit further, but definitely for n equals to 500 or for n equals to 100, this is no longer possible. So the other very general approach is Monte Carlo or quasi-Monte Carlo. So again, this is extremely general. I mean, whenever you have something like this, you can use this method. And compared to the PDE method, it does not have a curse of dimensionality, so in some sense, it doesn't really matter what the dimension is. This is only true to some extent, but anyway. Of course, the big disadvantage is it's slow. It's very slow. So for Monte Carlo, the rate of convergence, square root rate of convergence. For quasi-Monte Carlo, 1 over n, but this is still not very nice. Then there are 2 special methods which are not so general, so which only work in specific cases, but when they work, they are typically very fast. So one is the Fourier transform. So in some sense, the idea is you write this as the integral of f times the density of S, and then you use something like a Blancherel identity to rewrite this as the integral of the product of the 2 Fourier transforms, if you know the Fourier transform of the density, which is the characteristic function of S. Then what you see is that in fact you can realize this thing by a fast Fourier transform, FFT, and since fast Fourier transform is, as the name says, very fast, this works very well when it is possible. So drawback is this only works when you know the characteristic function explicitly, or let's say semi-explicitly, and also you suffer from the curse of dimensionality. And finally, approximation formulas. So generally, approximation formulas means that you use some parameter here, either the model, some parameter of the option or the model, and you do some asymptotic expansion in this parameter. Could be something like a large strike expansion, saying that k goes to infinity, or could be, I don't know, a small volatility expansion, meaning that the volatility, the variance, so to say, goes to 0, or in our case it will be a short time expansion, meaning that the capital T goes to 0. So you try to derive an asymptotic expansion, and then you just use this formula, for the non-asymptotic case, and you only even consider this if the resulting formulas are very fast to evaluate, otherwise there's no point. But of course the drawback is this has to be derived on a case-by-case basis, so that's not possible for a generic model.
May I just ask? So I remember when I saw something like this many years ago, so it makes a big difference whether you're at the money or in the money or out the money. So at the money is the most complicated case and have logarithmic weights. So either method will be slow.
So in our case this is not true.
No?
So you will see that even at the money, strictly speaking, the formulas that I'm going to present do not make sense at the money because there is something like 0 divided by 0. But you can show that the thing converge. You go you go not precisely at the money, but an epsilon away, you get a nice result.
But at the money is a different rate than all the other cases. That's what I know.
So, we have an extension of this work which I'm not going to talk about now for the at the money case, and indeed you have to go in the heat kernel expansion that I'm going to talk later, you have to go one step further, so you have to add one further higher order term to get the expansion, but then it works nicely. And numerically you don't see a difference. It's more the out of, for our particular case, it's more the far out of the money case which makes problems. But you're right, at least you always have to consider at the money and out of the money separately. Let's talk about the setting first that we are really working in. So we consider the so-called local volatility model, which means nothing like this. So you have n stocks. For the specialists, we use forward prices, which allows us to ignore interest rates here. Dynamics of the stock really depends only on the individual component. We have a Brownian motion, and these guys are coupled by the correlation of the Brownian motion. So the Brownian motion has a non-trivial correlation. I have said this already, so the goal is to compute the expectation of an object like this. Now let me give you two examples. The first example is of course the Black-Scholes model, which is included as a special case here. So that would be that sigma is a linear function. And okay, in principle of course you know the distribution of the solution. It's a log normal, so we have a big vector of correlated log normally distributed random variable. Even in that case, computing such an expectation is far from being a simple problem. And actually, if you look in the literature, even quite recently, you will find research papers on treating this case, for instance, in dimension 5 or something like this. So of course in dimension 1 it's trivial, in dimension 2, 3, in low dimensions it's easy to do it numerically, but in very high dimensions this is very difficult. The other problem, the other specific example, and this is the one that we are going to consider in the numerical example session, is the so-called CEB model, where you have here such a fractional power and the beta is between 0 and 1. So we allow for anything between 0 and 1, I should say. And this is important because, well, I will say a little bit further. So, in the first step, what I'm going to try is I'm going to try to decompose the expected value of this guy into two terms. The first term is the so-called intrinsic value of the option. That is, you just plug in the initial value for the f's in here. And typically this is a big part of the price of the option. And then there is the remaining term. And since there is no problem, of course, I mean the intrinsic value is known, no problem in doing numerics here. So we just concentrate on the remaining part. And for this, the first thing to consider is, well, we consider just the basket itself. Of course, it is a stochastic process, it has some dynamics, but note please that this one-dimensional process, this dynamics is not a Markovian dynamics or anything, because the right-hand side depends on the individual components Fi and not just on the weighted sum, not just on the index. So we plug in the payoff function and we formally apply an eta formula. Of course, this guy here, this positive part function is not differentiable, so really what you would need to do is an Ito Tanaka formula, which gives you a local time, but formally what you get is something like this. So here this should be something like a delta function, just concentrated on the point here, and the kink. Right. So next you apply the expectation, and what you see is that this guy here is a martingale, so it drops out. And what you are left with is, and this is actually this kind of decomposition that I was talking about, is the intrinsic value plus something which is going to be an integral over this manifold here. And in the last step, what we're going to do is we rewrite this expectation as an integral with respect to the transition density, and what you get out is something like this. This is known as the Carr-Gerald formula in the literature. So note that this, from the outset, this doesn't help us very much because, well, we still have a very high dimensional integral. Okay, maybe the dimension is 1 lower than before, but the difference between 100 and 99, for instance, is not that big. And secondly, of course, we have no idea what the transition density function is. And these are the two approximations that we are going to use. On the next slide, we are going to approximate the transition density by something which we know, and we then are going to approximate the integral. So let's first talk about approximating transition density, and this is by the so-called heat kernel expansion. So I will talk in more detail about this formula in a few minutes. For now, what I want to stress is that the function d here is something like a norm, like a metric distance, but not in the Euclidean metric, but in the metric which is induced by the diffusion. And then there is some other term which is not so central, but if you just look here, this looks almost like a Gaussian density. You ignore the second term. Okay, and in particular note that if t is small, this guy here is concentrated around the minimizer of the minimum of this d squared function. I mean, f naught here is of course fixed, it's the initial value, and f is the variable. So we are going to apply Laplace method for integrating this guy, and Laplace method basically means you do a Taylor expansion around the minimizer f star here of the d function. Since f star is the minimizer, the first order term is 0, so you start out with the second order term, and the second order term is basically with respect to the Hessian matrix Q here, but now this is, if you ignore the higher order terms, this is really a Gaussian density, so you can compute this thing, and what you get out is some function like this, right? And then you have the square root of the determinant of Q as usual for, and Q is a covariance matrix for a Gaussian. So there are of course some issues here. I mean, if you want to do this rigorously. And the main issue is, and the reason why we cannot really do this rigorously, is that the models that we consider have very bad behavior close to the boundary. And boundary in this case means when one of the components becomes 0. So what I mean by this is, think about, for instance, the CEV model. And if beta is smaller than 1, this guy is not differentiable at 0. And it's even worse, because if beta is smaller than a half, what happens is that you actually even get the point mass at 0. So the boundary will be attained, and even in such a way that you get really a positive probability of the f being equal to 0. So in such a case, such an expansion breaks down. And this is the reason why actually for such local volatility models, well, unless this has only been rigorously established for very, very special cases, and also for 1 or 2 dimensional cases only. So this is a difficult problem. So, and it's so prominent in some way that there is even a name for this kind of argument, and that is, well, we rely on the principle of not feeling a boundary. So the idea is we have to start far away from, I mean, we have to start sufficiently away from the boundary that the probability of ever hitting the boundary is so small that all these effects from the boundary will not disturb our result. And this matters actually, I should say, because if you consider equity like we do here, this is a reasonable assumption. If you consider interest rate modeling, this is a much more problematic issue. So there it will often these kind of expansions will fail.
If n is 50 or 100, so
Yes.
how do you compute reliably the determinant of q? That's model dependent, right?
It's no problem, I would say. I mean,
Well, it depends on the model.
yes.
So
Okay,
the model,
are you
you
saying
have
that,
precise model at 100 dimensions.
Are you saying that, okay, I'm assuming that I'm given the correlation matrix.
Oh, okay, that's easy.
Of course, getting the correlation matrix is a different issue. Okay, so what you get in the end is something like this. I still call it a theorem, even though I cannot prove that. And I mean, the specifics is not really important. But this is not the end of the story, because in the next step, what you do is you express this expansion as an expansion into implied volatilities. So what does it mean? You take, for instance, the Black-Scholes formula in terms of this one-dimensional variable, in terms of the index, and you plug in such an ansatz for the volatility in the Black-Scholes formula. You compute the corresponding Taylor expansion of the Black-Scholes formula, and then you compare coefficients with this guy upstairs, and this allows you to actually get formulas for sigma 0 and sigma 1 here. So I've written down the formula for sigma 0 explicitly. The formula for sigma 1 is a little bit more complicated, but similar in style. And we also do this for the Bachelier model. Okay. And as a matter of fact, I should say here, this is not just being fancy, it's also, it's empirical, is well known, and also in this case, you can see that this improves the quality of your formula. So the error, if you plug in these guys in the Black-Scholes formula, the error will be considerably smaller than if you directly take this formula here. So, the next few minutes I want to explain you a little bit more about this heat current expansion, which is really the fundamental basics of this paper. Of course, this is I mean, let's start first with the notion. What is the heat current? So for this I want to consider a general diffusion model like that. Attached to it is its infinitesimal generator. Of course, this is very standard. And the heat kernel is the fundamental solution of the corresponding parabolic equation. Or in probabilistic terms, it's the transition density of the process X. This is the same thing. And heat kernel in physics, or mathematical physics, is a very, very classical object, very well studied. And also the link between the heat kernel and the geometry is a very classical subject, going back to the 40s. There is a very, very nice paper by Katz from '66, which is titled, "Can You Hear the Shape of the Drum?" And this really, very catchy phrase, but it really shows what's going on and why this is important. So here the situation is a little bit different, because here the operator is just the Laplacian. So you consider just the drum in motion, but you consider it on some non-trivial domain D. In our case, D is Rn, essentially. So it's a trivial domain. Here it's non-trivial. And what you want to relate is geometrical properties of the domain with the so-called partition function. So gamma are the eigenvalues on the Laplacian on the domain D. And in that case, the heat kernel, is just an auxiliary tool, which allows you to, and in some sense, I think these two guys are equivalent. So, and that shows you why this catchy title, because what can you hear? Well, you can hear the eigenvalues of the Laplacian. And what is your drum? Your drum is the domain. So you want to know, given the eigenvalues, what do you know of the domain? And in particular, there are some classical results, for instance, from Weil in '46, which shows this kind of expansion for the eigenvalues, where the volume of the domain appears. So one thing that you can hear is the volume of the drum. Another thing that you can hear is the surface of the drum. And actually, I mean, this is, I think, can you hear the drum? So, I mean, given the eigenvalues, can you determine the domain? As far as I know, the answer is, I mean, a few years ago, maybe 1 year ago, there was a nice talk at the VIAS by some specialist in this area. And if I remember correctly, if the domain is analytic, you can actually hear the domain. I mean, of course, up to translations and rotations and stuff like this. If the domain can have corners, you cannot hear it. And if you just, I mean, there could be two different domains which produce the same eigenvalues for the Laplacian. And for smooth domains, it's still unknown. It's a little bit different because we want to turn the whole thing around. So given geometric properties of the domain, we want to find out the heat kernel. And the second difference is, I already said that before, our domain has a very simple geometry, but our operator is more complicated. So in the first step, what we do is we make the geometry more complicated in such a way that the operator becomes the Laplacian again. And to do this, we introduce some specific Riemannian metric tensor, which is precisely the inverse of the diffusion matrix here. So if you do that, what you see is, okay, this is now a Riemannian manifold, so it has a geodesic distance, and the geodesic distance is precisely the function d from before. So instead of the Euclidean distance that you are used to for the Gaussian measure, you just take this new geodesic distance, and it also has attached to it the Laplace-Beltrami operator. I mean, the formula is not so really important. And what you see is that up to some change in the drift term, your operator L, the generator of your diffusion, is really the Laplace-Beltrami operator on this Riemannian manifold, well, plus some extra drift term. So in other words, as seen from this geometry, we are really considering a Brownian motion with drift. And a Brownian motion with drift, well, this should suggest that the density should really look something like this. So let's first look at the last term here. So this is really like the Gaussian density, except that we don't use the Euclidean distance, but the distance induced by the diffusion, the Riemannian distance and the Hamilton. Now, that's not the whole truth, because first of all we have the drift, and even if we did not have the drift, the density of the Brownian motion in this geometry is not equal to that. So you have some correction terms to that. And finally, the first term here, this is again simple because this is just something like a change of measure from the Riemannian volume measure to the Lebesgue measure again. So we want to consider everything in the Lebesgue measure. And these guys here, these are the so-called heat kernel coefficients. I don't want to go into details here. I mean, there are formulas, at least for the zero-order term. There are various nice formulas. If you go higher, the formulas become very complicated, and it's actually an active area of research, especially away from the diagonal. I mean, when you consider x naught, then everything is rather simple, even when you go higher up, but away from the diagonal, this is not so easy. Maybe one remark here, everything is given, well, in a zero-order case at least, everything is given in terms of geometric properties. For instance, here there are some geodesics appearing. You have the second derivative of d squared. And actually, if you go a little bit more into things, you will see curvatures appearing and similar quantities of the geometry. Okay, so what makes the local volatility case special? I mean, everything here is quite generic. The only thing that you need is you need to be in something like a uniformly elliptic case, so you need that your diffusion matrix always is invertible. But otherwise, this is very general. Well, the special thing about the local vol case is that in that case, this geometry is actually isomorphic to the Euclidean geometry. And actually, you can make this isomorphism explicit. And the formula is like this. So if you transform from f to the x, given in these two steps here, then what you find out is that the L is transformed into the standard Euclidean Laplacian plus some extra drift term. So and that means, for instance, if you're interested in the square distance function in this geometry, what you do is you do this transformation, then you compute the Euclidean square distance function. If you're interested in geodesics, well, you take a straight line and apply the inverse transformation, and you get a geodesic. So all these things are explicit. And actually in the CEV case, you can see that all these integrals, which are actually now one-dimensional integrals, so in principle could always be quite easily computed numerically, but in the CEV case, all this is completely explicit. So this is the special thing about local vol and also about CEV, I should say. So finally, we have to justify all these binomial examples, because I told you that we cannot prove these expansions, and even if we could prove it, I mean, after all, we are doing numerics here. Even if it works in theory, if it doesn't work in practice, this is not very good. But before showing you some pictures, I want to show you, try to give you a little bit of intuition to the problem. So what is here? What is here is you take a three-dimensional case, and what I plot here are the implied volatilities for the individual components, the red, the blue, and the green line, and the implied volatility in black of the full basket. So what you see here is the weights here are equal to 1. All the weights are equal to 1. So what I want to point out here is that the implied volatility of the basket is quite different from what you would expect. I mean, it's not just the average implied volatility of the individual components, it's considerably lower than that. So, and this is also a stylized effect. Here, this is a very interesting plot. Well, the plot here is the optimal configuration. It's the f star, the minimizer for the distance function. So here on the x-axis there are different baskets, and on the y-axis there's this corresponding minimizer. So remember, the situation is like this. You start with some f naught, and for a given k, there is some manifold, which is the manifold of all the f, such that some Wi Fi equals k. So this is of course a linear manifold in the Euclidean space, but in the transform space this is no longer linear. It's actually also not, I mean it's something like, it's not a polynomial either, so it's quite complicated, nonlinear. And then there is the f star is the point on this manifold with the smallest distance to f naught. And there is a nice interpretation, namely the interpretation is you start out with an option which is, say, well, it's the most likely point on this manifold that you could get to from starting from the f naught, if you condition on the fact that you go there to begin with. So it's the most likely configuration. So this is, and actually you can make this precise. Okay, so what does this mean? Let's consider, let's go far outside. So the k is very large, we are deep out of the money. But we condition on the fact that at the end of the day, we are going to be precisely at the money. So obviously, all the individual components have to increase. All of them have to increase. But there is one, the right one, which has to increase the most. And why is that? Because if you look a little bit closer, especially here on the beta and on the sigma, this one is the one with the highest volatility. So all of them have to increase, but the one component with the highest volatility increases the most. This is the most likely way how this option could actually go into the money. Very intuitive. But now let's consider some numerical results. So here, I mean, I'm presenting a cross-section. We have many results in the paper and even more that we have not put in the paper. Here's some kind of a cross-section. So I consider 4 different cases in 4 dimensions. Dimension 5, dimension 10, 15 and 100. And we consider 1k, 1 strike price each, and we consider time to maturity half a year, 1 year, 2 years, 5 years and 10 years. And then I normalize the error in a sense that I take a relative error and I divide by something like the squared volatility times t, to make it kind of dimension independent. Okay, and what you see is for the 0 order asymptotic prices, that is just taking the sigma naught, you see something like this. And this is actually what you would expect, because roughly speaking these guys are constant in time. And constant in time due to this normalization means that they actually decay, the errors decay linearly, and this is precisely what the asymptotic predicts here in this case. It's not completely true everywhere, and I should also say here in the 100-dimensional case the problem was that it's very difficult to get reference values. I mean, we use some kind of quasi Monte Carlo plus some variance reduction techniques and some high order scheme for solving the SDE, but in dimension 100 this is quite tough. Okay. Now let's go to the first order term. First order term is a bit misleading because really the error is then second order, and this is also shown because roughly speaking, if you consider for instance the first column here, when you double the time, the error also doubles. Okay, but what is interesting here is the size of the error, because it's really very small, very small. Also, I should say what I found quite fascinating is, 10 years, this is a short time expansion, and 10 years is still small enough that you are in the asymptotic regime somehow. Of course the error becomes bigger, but it's still quite small, and it still behaves like it should be, right? You go from 5 to 10, roughly the error doubles. This is quite amazing. Now, consider some plot. Now this is in dimension 3 again, I think, or 4, I'm sure. Actually what you see here are the prices, again forward prices for the specialists, for the 5 different maturities, and actually there is a second curve, and that is the first order prices, but you cannot distinguish them visually. So let's consider local relative errors instead. So the dashed lines are the 0 order local relative errors, and the solid lines are the first order relative errors. And again, I mean, take for instance the red one, which is t equals to 2, you see that the relative error is smaller than 10 to the minus 4 here every time. And also I should like to mention that this kind of right behavior is due to the reference solution. So the Monte Carlo error is the order 10 to the minus 5 here, and you see it. Also I should like to mention that, you know, this is a very wide variety of maturities. So you go from very deep in the money to very deep out of the money, and the performance is more or less uniform. It increases because, you know, the price decreases here, and since we consider relative errors, it means that you divide by smaller and smaller numbers, right? That's really the reason why you have this increase, a slight increase of maturities. And okay, maybe just. There's also, you can do similar things for the Greeks, for the derivative of the whole thing, but this is work in progress and I don't want to say too much about this. And with that, I thank you very much for your attention.
Question or remark?
What are the difficulties to prove the expansion in the theory?
Well, the difficulty is to prove the heat kernel expansion to begin with, and the difficulty is the boundary. I mean, say if you have, okay, let's put it like this. For instance, there's a very nice paper by Yoshida in the 50s. He proves the heat kernel expansion for compact Riemannian manifolds. There, everything works very nicely. Now, there are other proofs where, you know, you can remove this compactness, but I mean, let's put it like this. You cannot even define your Riemannian metric on the boundary, really, right? And also, you know that it's not true because you know that, say, you know that you don't have a density. It doesn't exist, right? Really. So you could, I mean, okay, why does it work? Because there is an exponentially small probability to hit the boundary, and also, like, if you, I mean, in this local volatility case, if you consider like balls in the Euclidean, you transform them with this isomorphism. They are, how do they call this? They are geodesically closed, meaning that any geodesic connecting two guys doesn't leave the ball. So you expect that you have no bad influence from the boundary going inside due to the geodesics. I mean, what I'm trying to say is, in principle, what you would fear is that, you know, you have 2 points with a boundary of 2 points which are far away from the boundary, but somehow if the geodesic between those 2 points would look like this, you are in trouble. But this doesn't happen really. So I think that's the reason why it works, but I'm not sure how to make this argument rigorous.
Maybe one question or remark. So you mentioned once a Laplace expansion, and I guess it was on the slide 8. You showed it. Yeah, something like this. And so people doing vegetation from Mises, expansion from posterior, so probably should know that the proof is also given. First rigorous proof given by Laplace by very similar arguments. So somehow related, all of this is related to some the conditional of multivariate normal is normal.
Okay, I didn't know that.
And so I mean, even if you do it over some truncated domain, it's still if you properly truncate it. So if the Gaussian measure, conditional Gaussian measure of your domain, so this is the idea of this trick with Einstein to Mises. So maybe you can use similar arguments.
I I should also maybe add a remark, and that is one reason why it works so well is that you don't have a drift here. So you have a martingale.
So it's drifted, it could hit the boundary.
Yes, but with drift, even this kind of expansion wouldn't, the heat kernel expansion wouldn't be so good.
Why?
Why? Well, I guess because this kind of local argument doesn't work so well if you go further, very far in time. I mean, let's put it like this: if you have a big drift, you can definitely in 10 years you can go far away from where you started from in distribution.
Okay, so.
Yes.
Well, I complain about the title. There are many papers say beating Monte Carlo, but the point is that Monte Carlo is kind of a generic concept. So you can put Monte Carlo on top of your approximation. So you can, afterwards, after you run this approximation, you get the initial solution, kind of, and start Monte Carlo from there. It will still be better. So you can take Monte Carlo on top.
I absolutely agree, and actually I'm surprised that this is the first time that I'm, that somebody complains about the title, because this was the idea of my co-author, and I was quite hesitating to put this title. Of course, it's. As I was trying to say, you're absolutely right. Monte Carlo is a generic method. You cannot fairly compare these two things.
What is meant is plain Monte Carlo.
Then you can always beat plain Monte Carlo. That's right.
So this is how you should understand.
But the thing is, if you go do it in, actually I have not tried it in 500 dimensions, but in 100 dimension, computing this asymptotic formula in a plain R script without any optimizations takes 2 seconds. And for the reference values, we have to wait like 2 weeks in the high dimensional case, right? And even then, the error is considerably larger.
What I mean is that you can take your reference that you get now and then start in Monte Carlo from there, and you can improve kind of with a typical rate. So that would be reasonable to do.
Yes. On the other hand, I'm absolutely agree. On the other hand, I think for all practical purposes, this is good enough. The accuracy is good enough.
Okay, I think we thank Christian once again.